Hi everyone, welcome to AS Engineering College YouTube channel. I'll welcome to the series of lectures on the course Discrete Mathematics. In today's session, I'll be discussing on the following topics. The first one is special connectives. In addition to the connectives which we have discussed in the previous session, we have two more connectives and they are NAND and NOR connective. NOR connective, NAND connective. These two are called special connectives. So we'll be sorry for the small technical issue. Welcome to the AS Engineering College YouTube channel and welcome to series of lectures on the course Discrete Mathematics. In today's session, I will be focusing on the following topics. The first one is special connectives. In addition to the connectives which we have discussed in the previous session, today I am going to explain two more connectives, NOR and NAND connectives. These are called special connectives. Next we have logical implication. I will be focusing on logical implication after the special connectives. Then I will be discussing on normal forms. There are two types of normal forms. One is disjunctive normal form. The other one is conjunctive normal form. After normal forms, there are some laws of logics. We will be discussing on laws of logic. Then we have principal normal forms. Like normal forms, there are two kinds of principal normal forms. The first one is principal disjunctive normal form. The another one is principal conjunctive normal form. So after these principal normal forms, we will be discussing on arguments and then we will be discussing on consistent and inconsistent premises. These are all the topics which I am going to explain to you guys. Now I will see the first one, special connectives. Now in previous session I explained the connectives, negation, so which is obtained by the connective NOT. There are some connectives. I explained 6 connectives. First one is NOT connective. By using NOT connective, we will be obtaining a compound proposition called negation. Then we have AND connective. By using AND connective, we will be getting the compound proposition conjunction. Next we have OR connective. There are inclusive OR and exclusive OR. Inclusive OR is nothing but just OR. By using OR, we will be getting a compound proposition called disjunction. Then we have exclusive OR. By using exclusive OR, we will be getting exclusive disjunction. Then we have if-then connective. By using if-then connective, we will be getting conditional statement. And the last one is if and only if. By using if and only if, we will be getting biconditional. So these are all called logical connective. We have NOT connective. By using NOT connective, we will be getting a compound proposition called negation. This is a symbol which we use to denote NOT connective, either this one or this one. Next, by using AND connective, we will be getting a compound proposition called conjunction, and this AND connective is denoted with this symbol. And then we have OR connective. By using OR connective, we will be getting a compound proposition called disjunction, and this OR connective is denoted like this. Exclusive OR. By using exclusive OR, we will be getting exclusive disjunction. This exclusive OR denoted with the symbol this. And next one is if then. if then is denoted like this. This is a symbol which we use for the conditional statement, and this one is biconditional. By using if and only if connective, we will be getting a compound proposition called biconditional. So these are all called logical connectives: not connective, and connective, or connective, exclusive. Or can be taken in two senses. One is inclusive sense, which is nothing but just or, and the other one is exclusive or, and then if then connective, and if and only if. These are all called logical connectives, and these are the compound propositions which are obtained by using these logical connectives, and these are the symbols which we use to denote the logical connectives. In addition to these logical connectives, we have two more connectives, and they are special connectives. These special connectives are two types. One is NOR connective, and the second one is NAND connective. First we discuss about NOR connective, and then we discuss about the NAND connective. So now first is NOR connective. This NOR connective is negation of OR connective. So as I explained the OR connective, if you take the negation of the OR connective, then you will be getting the NOR connective. Next, this is the definition of NOR connective. For any two propositions P and Q, the compound statement negation of P or Q is denoted by P NOR Q. This is the symbol which we use to denote the NOR connective, and is read as not P or Q. So as I told you, NOR is the negation of OR connective. By using OR connective, we will be getting this compound statement. For this compound statement, if you take the negation, then we will be getting the NOR connective. So thus, this NOR connective is defined like this. This is a symbol used for denoting the NOR connective. Now, NOR is a combination of NOT and OR. So this is a combination of NOT and OR. Next, thus P NOR Q is negation of P or Q. P NOR Q is negation of P or Q. So here NOR is a negation of OR connective. NOR is a combination of NOT connective and OR connective. NOT connective and OR connective. So if you take the negation of OR connective, then we will be getting this NOR. The symbol which we use to denote the NOR connective is this. This is symbol we use to denote the NOR connective. Now we will see what is the truth table of NOR connective. So here I am taking two simple statements. P is one statement, Q is one statement. When we take two simple statements, we will be having 2 power 2. 2 power 2 is nothing but 4 possible truth cases. Now I am writing all those possible truth cases one by one. True, 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 false, false, true, false, false. These are the 4 possible cases for two simple statements. Then I am finding the disjunctive statement, P or Q. Then I am finding the disjunctive statement P or Q. Then I am taking the negation of this, negation of P or Q. The NOR connective is negation of OR connective. First I am finding the P or Q. This is the disjunctive statement. By using OR connective, we will be getting the disjunctive statement. If you take the negation of this, then you will be getting the NOR connective. So this is denoted like this, P NOR Q. P NOR Q. So this is the NOR connective. Now look at. So this is the disjunctive statement. The disjunctive statement is false when both the statements are false. Both in the sense when P is false and Q is false. So out of these 4 cases, look at the last case. In the last case, the statement P is false, Q is false. Therefore, their disjunctive statement P or Q is false in this case only. In the remaining 3 cases, it is true. The conjunctive statement is true. In the remaining 3 cases, the conjunctive statement is false. In only one case, that is when P is true, P is false and Q is false. Now we will find out the negation of this disjunctive statement. When this is true, the negation of this is false. When this is true, the negation of this is false. Next, the negation of this is false. The negation of this is true. This is the truth table for NOR connective. So here I am taking two simple statements. One is P, another one is Q. Then I am finding the truth values for the disjunctive statement, and then I am finding the truth values for the NOR connective. This is the truth table for the NOR connective. Now we will see the next special connective, that is NAND connective. So the next connective is NAND. NAND is nothing but negation of AND connective. Negation of AND connective. So NAND is nothing but negation of AND connective. So it's a negation of AND connective. Now we'll see what is the definition of NAND connective. So here I am taking two simple statements, P and Q, and the compound statements negation of P and Q is denoted by like this. This is the symbol we use to denote NAND connective, and is read as not P and Q. So the negation of AND connective is the NAND connective. By using AND connective, we will be getting the conjunctive statement. If you take the negation of it, then you are going to get this compound statement. This compound statement is read as P NAND Q. Here, this is the symbol which we use to denote the connective, non-connective. Here, this is a symbol which we use to denote the NAND connective. Then next point, NAND is a combination of NOT connective and AND connective. If you look at this statement, this is NOT connective, this is AND connective. So NAND is a combination of NOT connective and AND connective. Now this is NAND connective. So P NAND Q is equal to negation of P and Q. Now we will see the truth table for NAND connective. So here, like I am taking two simple statements, that is P says statement, Q statement. Then I am finding the truth values for P and Q. Then I am taking the negation of P and Q, which will give you the NAND connective. This is nothing but P NAND Q. So as usual, if there are two simple statements, then there will be four possible truth cases: true, 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 false, false, true, false, false. There are four possible truth cases. So this is the conjunctive statement. This is the conjunction of two simple statements P and Q. The conjunctive statement is always true when both P and Q are true. If you look at these four cases, in the first case, both P and Q statements are true. In all other cases, both of them are not true. Therefore, this conjunctive statement is false in the second case, third case, and fourth case. So these are the truth values for the conjunction of P and Q. Now I am taking negation of this conjunctive statement. So when we are finding the truth values of negation of some conjunctive statement, if this conjunctive statement is true, then its negation will be false. This is false, its negation will be true. This is false, its negation will be true. This is false, its negation will be true. So this is the truth table for the special connective, NAND connective. NAND is the negation of AND connective, and a NAND connective is combination of NOT and AND connective. NAND is nothing but negation of AND. So this is the symbol which we use to denote the NAND connective. So this is the truth table for NAND connective. These two are the special connectives. We have only two special connectives. One is NOR connective and the second one is non-connective. Now, next we will see the logical implication. Under this logical implication, we will be discussing about hypothetical statements or implicative statements. Hypothetical statements are implicative statements. Now let me explain one thing. In the previous session I explained about implication. This implication is also called conditional. This implication is also called conditional. So, if you take the two statements u comma v, then its conditional statement is denoted like this, u conditional v, u conditional v. It is read as u conditional v. This u conditional v is false when u is true and v is false. In this is false. In this case only this conditional statement is false. So, here this is implication. This implication is different from the logical implication. Logical implication and implication, both of them are different. I will explain how both of them are different. So, this implication is also called conditional statement. If you take two statements u and v, then this is a conditional statement. It is read as u conditional v. U conditional v statement is false only when u is true and v is false. In all other cases, the conditional statement is true. Now, I will explain what is logical implication. So, here I am taking one example. Before I am going to explain about the logical implication, let me give you one example. So, that example is, I am taking two examples. Examples 1. I am taking P statement, 2 is even integer. 2 is even integer. Next, I am taking one more statement, Q is Hyderabad is in Telangana. Hyderabad is in Telangana. Is in Telangana. So, now look at these two statements. 2 is an even integer. Yes, 2 is an even integer. That means the truth value of this is 2. Hyderabad is in Telangana. Yes, Hyderabad is in Telangana. Therefore, the truth value of this is true. Now, I am finding P conditional Q. So, P conditional Q is, so how to get the P conditional state Q? P conditional Q is obtained by combining P and Q using the logical connective if then. So, this is if 2 is even, then Hyderabad is in Telangana. This is one example. So, now here P statement is true, Q statement is true, therefore, this is true statement. The conditional statement is true. Now, I will give you one more example. P is 3 is odd integer, or else I will change this like this. 4 is odd integer and Q is, the statement Q is Hyderabad is in United States of America. Now, I am finding the conditional statement P conditional Q. If 4 is odd integer, if 4 is odd integer, then Hyderabad is in United States of America. United States of America. Now, I will find out the truth value of this. So, here P statement is false, Q statement is also false because 4 is not a odd integer and Hyderabad is not in United States of America. So, both the statements are false. Now, the truth value of P conditional Q is true. I told you when we take a conditional statement, P conditional Q is false when P is true and Q is true. When P is true and Q is false. Q is false. So in this case only the conditional statement is false. The P conditional Q is false when P statement is true and Q statement is false. In all other cases, the conditional statement is true. In this case only it is false, in the remaining cases it is true. Now observe these two examples. P conditional Q, this statement is true because in this case P is true, Q is true, therefore the conditional statement is true. In this case also the conditional statement is true. Now I read the sentences, statements. If 2 is an even integer, then Hyderabad is in Telangana. Whatever conditional statement I have written, that is logically true. Similarly, if 4 is an odd integer, then Hyderabad is in United States of America. So this is also logically true. This statement is logically true and this statement is logically true. If you look at them, they don't have any sense. These two statements doesn't make any sense. We will not use these type of statements in future. These type of statements will not be useful for us. So here, even though P conditional Q is logically true, this doesn't have any sense. For Hyderabad to be in Telangana, 2 need not be even integer, right? For Hyderabad is in United States of America, 4 need not be odd integer. If you look at both the conditional statements, there is no relation between P and Q, but they are logically true. So we don't want to study this type of statements in future because these type of statements will never be useful for us. So we want to have the conditional statements in which P and Q are related to each other and the truth value of P is depending on Q and the truth value of Q is depending on P. Then such type of conditional statements are called hypothetical statements. Look at this. So if a conditional, we are going to study the conditional statements P conditional Q such that P and Q are related to each other and the truth value of P is depending on Q and the truth value of Q is depending on P. So such type of statements are called hypothetical statements. Such type of statements are called hypothetical statements. So what is hypothetical statement? Hypothetical statement is a conditional statement in which P and Q are related to each other. P and Q are related to each other, which means the truth value of P is depending on Q and the truth value of Q is depending on P. If you study that type of hypothetical statements, those will be useful for us. So from now onwards, we are going to study the conditional statements in which P and Q are logically related to each other, which is nothing but P, the truth value of P is depending on Q and the truth value of Q is depending on P. Such type of statements are called hypothetical statements. Such type of statements are called hypothetical statements. So hypothetical statement is a conditional statement in which P and Q are, the truth values of P and Q are related to each other. Now we'll see what is logical implication. So this logical implication is defined for the hypothetical statements. The hypothetical statements are also called implicative statements. So to define the logical implication, I am taking one hypothetical statement. What is hypothetical statement? A conditional statement in which the truth value of U and V are related to each other. So this hypothetical statement is such that the truth such that V is true whenever U is true. V is true whenever U is true. Then we say that U is logically imply V or U is tautologically imply V. So when we say that U is logically imply V, whenever U is true, V must be true. Whenever U is true, V must be true. Assume that whenever LHS part U is true, if V is also likewise true, then we say that U is logically imply V. Symbolically, this is denoted like this. U is logically imply V. So when we say that U is logically imply V, whenever U is true, V must be true. Whenever LHS is true, if RHS is also true, then we say that U is logically imply V. This logical implication is also called tautological implication. Tautological implication. Suppose whenever U is true, if V is not likewise true, then we say that U does not logically imply V, and it is like denoted like this. Whenever U is true, if V is also true, then U is logically imply V. Whenever U is true, if V is not true, then U is not logically imply V. This is the logical implication. This is the notation for it. This is the logical implication. So logical implication is defined for hypothetical statements. Hypothetical statements, U conditional V is such that whenever LHS is true, if RHS is also likewise true, then U is logically imply the RHS V. Otherwise, U does not logically imply the RHS V. Now, I will see some examples. So, I am taking some example. So, this is the LHS, let it be U, and this is the RHS V. So, now we have to verify whether whenever U is true, RHS V is true or not. For that, we have to construct the truth table. So, here I am taking two. If you look at these two U and V are involving only two simple statements. I am taking two simple statements. This is P and this is Q. Next I am finding the truth values for P conditional Q, and then I am finding the truth values for U is equal to P and P conditional Q. P and P conditional Q. So there are two simple statements. We will be having 2 power 2 is nothing but 4 possible truth cases, and those 4 possible truth cases are true, 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 false, false, true, false, false. These are the 4 possible truth cases. Now, what is this? This is the conditional statement. This conditional statement P conditional Q is false when P is true and Q is false. In all other cases, it is true. So, out of these 4 cases, look at the second case. In the second case, P is true and Q is false. In this case only it is false. In the remaining cases, it is true. So, these are the truth values for P conditional Q. Now, this one, what is this one? P and P conditional Q, which means I am finding the conjunction of this one and this one. The conjunction of P and P conditional Q is nothing but P and P conditional Q. This conjunctive statement is true when both of them are true. If you take any conjunctive statement, the conjunctive statement will be true when both the statements are true. So, here when P is true, P conditional Q is true, then P and P conditional Q will be true. If you observe the first case, yes, P is true, P conditional Q is also true, therefore it is true. Second one, P is true, P conditional Q is not true, therefore it is false. Third case, no, P is false, therefore it is false. And the last case, P is false, therefore it is false. So, in the 4 cases, only in the first case, P and P conditional Q is true, therefore their conjunctive statement P and P conditional Q is true. Now, these are the truth values for the LHS. Now, what is RHS? RHS is V. RHS is V. Now, what is the definition of logical implication? Whenever LHS is true, RHS must be likewise true. Whenever LHS is true, RHS must be likewise true. So what is the LHS? This is the LHS. Whenever P and P conditional Q is true, then Q must be true. So in out of 4 cases, only in the first case P and P conditional Q is true. In this case only you need to verify whether the RHS V is true or false. The RHS V is true in this case. That means whenever this LHS is true, the RHS is also likewise true. Therefore, we say that P and P conditional Q is logically imply Q. P and P conditional Q is logically imply Q. So this is how we are going to prove whether U is logically imply V or not. Now look at this. If you take P also, whenever this P and P conditional Q is true, P is also true, which means this LHS is also logically imply P. That LHS is also logically imply P. Now look at, whenever this is true, P conditional Q is also true. P conditional Q is also true. That means this LHS is logically imply P conditional Q also. That means the LHS is logically imply Q, it is logically imply P, and it is logically imply P conditional Q also, because whenever this conjunctive statement, whenever this U is true, this P conditional Q is also true, Q is also true, and P is also true. This is how we prove whether the LHS is logically imply RHS or not when 2 simple statements are given. For example, if 3 simple statements are given, then we will say how to test whether the LHS is logically imply RHS or not. So now this is one compound statement. I am taking this as U, and this is the other compound statement, and I am taking this as V. So then it becomes U conditional V. So here U is P and P conditional Q and R, V is P or Q conditional R. So now there are 3 simple statements. If you observe U and V, there are 3 simple statements. The simple statements are P, Q, R. When there are 3 simple statements, then we will be having 2 power 3 possible truth cases, that is 8 possible truth cases. Now I am going to write all those 8 possible truth cases one by one. P is true, Q is true, R is true. P is true, Q is true, R is false. P is true, Q is false, R is true. P is true, Q is false, R is false. P is false, Q is true, R is true. P is false, Q is true, R is false. P is false, Q is false, R is true. P is false, Q is false, and R is false. These are the 8 possible truth cases when 3 simple statements are given. Next I am going to find out the truth values of P conditional Q. That P conditional Q is false when LHS is true, RHS is false. That is when P is true and Q is false. If you look at the second case, in the second case P is true, Q is false, therefore it is false. Similarly, look at the third case also, fourth case. P is true, Q is false, therefore it is false. In all other cases, that conditional statement is false. The conditional statement is false when P is true and Q is false. In all other cases, the conditional statement is true. In this case it is true, this case it is true, this case it is true, this case it is true. In all other cases it is true. So these are the truth values for P conditional Q. Now I am finding the truth values for U. What is U? This one is the U. P and P conditional Q and R. This conjunctive statement is true when all of them are true. When all of them are true. So in how many cases all of them are true? Look at when P is true, P conditional Q is true, R is true, this conjective statement is true. That means you have to consider P truth values, P conditional Q truth values and R truth values. If these three are true, then that conjective statement is true. If you observe first one, P is true, R is true, P conditional Q is true, therefore it is true. In the second case, P is true, but R is false, therefore it is false. In the third case, P is true, R is true, but P conditional Q is false, therefore it is false. P is true, R is false, therefore it is false. Next, P is false, it is false. Next case, in all other cases, it is false. That means, in only first case, P, P conditional Q and R are having the truth values true. In all other cases, it is false. These are the truth values of the LHS U. Now, I will be finding the truth values of the RHS. So, now first I will find the truth values of P R Q. This is P, this is Q. P R Q is false when both of them are false. In the first case, both of them are not false, therefore it is true. Second case, both of them are not false, therefore it is true. Third case, both of them are not false, therefore it is true. Fourth case, both of them are not false, therefore it is true. Fifth case, both of them are not false, therefore it is true. Sixth case, both of them are not false, therefore it is true. If you observe the last two cases, in the last two cases, both of them are false, therefore the PRQ is false in the last two cases. Next, I am finding the truth values of V. So, what is V? PRQ conditional R. So, this PRQ conditional R is false when this PRQ is true and this R is false. When PRQ is true and R is false. In that case only it is false, in the remaining cases it is true. In the remaining cases it is true. That means you need to consider PRQ, you need to consider PRQ and next one is R. So, now I am going to identify the cases where PRQ is true and R is false. If you look at the first case, in the first case this is true, this is not. In the second case, PRQ is true, R is false, therefore it is false. Third case, no. Fourth case, PRQ is true and this R is false, therefore it is false. In the next case, no. In next case, yes, this is false because PRQ is true and R is false. Next, in the next case, no. In the remaining cases, it is true. In the remaining cases, it is true. So, now we have constructed the truth values. That means we found the truth values for the LHS and RHS. Now look at. So, now this is LHS, this is U and this is V. So, when we say that LHS is logical imply RHS, whenever U is true, the RHS must be true. So, I am identifying the true cases of the LHS. The LHS is true in the first case only. The LHS is true in the first case only. So, in this case only, you need to verify whether the RHS is true or false. In this case, if RHS is also true, then we say that LHS is logically imply RHS. So, I repeat, whenever U is true, in that case only, you need to verify whether V is true or not. If V is also true, then the LHS is logically imply RHS. So, for whatever problem they have given, the LHS is logically imply RHS. This is how we prove when three simple statements are given. If three simple statements are given, then there will be 2 power 3, which is nothing but 8 possible truth cases. This is about the logical implication. Next we see this is also important one. converse, inverse, contrapositive of a conditional statement. If any conditional statement is given, then we can find out the converse, we can find out the inverse, and we can find out the contrapositive of that conditional statement. Converse, inverse, and contrapositive of the conditional statement. So I am taking some conditional statement. The conditional statement is P conditional Q. This is the conditional statement. For this conditional statement, I am going to define the converse, inverse, and contrapositive. First we will see what is the converse. So for this conditional statement, this is called converse. Q conditional P is called converse. Next one is inverse. Negation P conditional negation Q is called inverse of the given conditional statement. The next one is contrapositive. Negation Q conditional negation P is called the contrapositive of the given conditional statement. So this is the conditional statement. For this conditional statement, this is the converse. Q conditional P is called converse. Negation P conditional Q is called inverse. Negation Q conditional negation P is called contrapositive. These three, converse, inverse, and contrapositive, will be found for the given conditional statement. Now we will see what is the relation between them. There is some relation between converse, inverse, conditional, contrapositive. Now I am going to derive the relation between them. So for that I am going to construct the truth table. So the truth table is this. This is P, this is Q, P conditional Q, this is conditional statement, Q conditional P, this is converse, negation P conditional negation Q, this is inverse, negation Q conditional negation P, this is the contrapositive. So this is conditional statement, this is converse, and this is inverse, and this is contrapositive. So there are two simple statements. Therefore there will be 4 possible truth cases: true, 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 false, false, true, false, false. So the conditional statement P conditional Q is false when LHS P is true and RHS Q is false. That means in the second case only it is false, in the remaining 3 cases it is true. Now this is the converse. This is also conditional statement. This conditional statement is false when LHS Q is true, RHS P is false. So in the third case, the LHS Q is true, RHS P is false. Therefore this is false in this case only. That is third case. So in this case, in the third case, it is false. In the remaining 2 cases, it is true. Next one. What is next one? Negation P conditional negation Q. I am finding the truth values for negation of P here. If P is true, negation P is false. P is true, negation P is false. P is false, negation P is true. P is false, negation P is true. Likewise, I am finding the truth values of negation of Q here. Q is true, negation Q is false. Q is false, negation Q is true. True, false. False, true. Now I am going to find out the truth values of negation P conditional negation Q. Negation P conditional negation Q is false when negation P is true and negation Q is false. So when negation P is true and negation Q is false. If you look at the third case, in the third case negation P is true and negation Q is false. Therefore it is false in the third case. In the remaining 2 cases it is true. In the remaining two cases, it is true. Now I am going to find out the truth values of contrapositive. Contrapositive is nothing but negation Q conditional P. Negation Q conditional P. So negation Q conditional negation P is false when negation Q is true and negation P is false. When negation Q is true and negation P is false. So in the second case, negation Q is true and negation P is false. Therefore, it is false in the second case only. In the remaining cases, it is true. In the remaining cases, it is true. So I have constructed the truth table for conditional, converse, inverse, and contrapositive. Now look at this. So this is the conditional statement, this is the converse, and this is the inverse, and this is the contrapositive. In last session, I explained about the logical equivalence. If two compound statements are given, U and V, we say that U is logically equivalent to V whenever both of them are having the same truth values. If U and V are having the same truth values, then we say that U is logically equivalent to V. So now observe, this is the conditional statement, these are the truth values for the conditional statement, and look at this. This is the contrapositive and these are the truth values of the contrapositive. True, true, false, false, true, 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 true. That means this conditional and this contrapositive are having the same truth values. Therefore, we conclude that P conditional Q is logically equivalent to negation Q conditional P. Negation Q conditional negation P. So this is conditional, that is contrapositive, that is conditional is logically equivalent to contrapositive. This is the first point to be noted. Now come to the second relation. So these are the truth values of converse and these are the truth values of inverse. If you observe the truth values of converse and inverse, both of them are having same truth values. Both of them are having same truth values. Therefore, we conclude that Q conditional P is logically equivalent to negation P conditional negation Q, which is nothing but converse is logically equivalent to inverse. Converse is logically equivalent to inverse. So from the converse, inverse and contrapositive of the conditional statement, we must understand that conditional and contrapositive are logically equivalent to each other and converse and inverse are logically equivalent to each other. This is the relation between them. Conditional, contrapositive. These two are logically equivalent to each other. Similarly, converse, inverse. These two are logically equivalent to each other. So this is the truth table for conditional, converse, inverse and contrapositive. Contrapositive and conditional are logically equivalent to each other. Converse and inverse are logically equivalent to each other. Now we will take one conditional statement. Now we will find converse, inverse and contrapositive of that conditional statement. So I am taking some conditional statement. If sun rises in the east, then 3 star, that is 3 into 7 is equal to 98. If sun rises in the east, then 3 into 7 is equal to 98. This is a conditional statement because sun rises in the east is the simple statement P, 3 star 7 is equal to 98. This is the simple statement Q. There are two simple statements. We are going to combine them by using if and then. by using if and then. When we combine two simple statements with if then connective, then we are going to get the compound proposition called conditional. This is the conditional of that. So, here the given statement is a conditional statement P conditional Q, where P is sun rises in the east, Q is 3 star 7 is equal to 98. Now, what is the converse of it? This symbol, this is the converse. What is converse? Q conditional P. What is Q? 3 star 7 is equal to 98. If 3 star 7 is equal to 98, then sun rises in the east. This is the converse for the given conditional statement. Now, the next one is inverse. Inverse is nothing but negation P conditional negation Q. You have to take the negation of P and you have to take the negation of Q. So, here what is P? Sun rises in the east. What is the negation of it? If sun does not rises in the east, if sun does not rises in the east, sun does not rises in the east is nothing but negation P. Then negation Q, 3 star is equal to 98 is Q. Negation means 3 star 7 is not equal to 98, which is nothing but 3 star 7 is not equal to 98. 3 star 7 is not equal to 98. Now, next contrapositive. Contrapositive means negation Q conditional negation P. So, this is Q. 3 into 7 is equal to 90 is Q. Take the negation of it. If 3 into 7 is not equal to 98, then negation P, sun does not rises in the east. Sun does not rises in the east. So, this is the conditional statement. For this conditional statement, this is converse, this is inverse, and this is contrapositive. This is how we have to find the converse, inverse, and contrapositive of the given conditional statement. Now, we will be moving to the next topic. So, normal forms. As I told you, there are two types of normal forms. One is disjunctive normal form. The second one is conjunctive normal form. The conjunctive normal form is nothing but CNF. Disjunctive normal form is nothing but DNF. Disjunctive normal form and conjunctive normal form. Now, first we will see the definitions of one by one in detail. So, this is the definition of this disjunctive normal form. So, you will be given some compound statement. You will be given some compound statement U. U is the compound statement. That statement will be given to you and you will be asked to find out the disjunctive normal form of it. So, V is some other statement. U will be given to you. You need to find out the disjunctive normal form of U, which is nothing but V, if V satisfies two conditions. If V satisfies two conditions, then we say that V is the disjunctive normal form of U. Condition number 1, V must be logically equivalent to U. That is, V must be logically equivalent to U, which is nothing but U and V must be having same truth values. Condition number 1. Condition number 2, V is a disjunction of two or more compound propositions, each of which is a conjunction involving the components of U or their negation. Now, let me give you one simple example. I am taking some U. U is equal to P and Q or R. That is one compound statement which is involving three simple statements. Now, I am expanding this. If you expand this, this is logically equivalent to, here I am using the distributive law. We will discuss the laws of logics in the future in next slides. So, if you expand it, then you will be getting P and Q or P and R. So, this is U, this is V. Already U is given and this is V. This is V. So, what is V? So, this is the given compound statement. This is the equivalent compound statement. Condition number 1 is satisfied. Now, look at the condition number 2. What is the condition number 2? V is disjunction. This is the symbol, R is the symbol. If you use R symbol, then you will be getting the disjunctive statement. Disjunction of two or more statements which are conjunction of components are their negations. So, here V is a disjunction of two compound statements. This is P and Q and P and R. If you observe 1 and 2 compound propositions, they are the conjunctions of the components. So, what are the components in U? P is one component, Q is one component, R is one component. So, this V is the equivalent compound proposition of U and V is the disjunction of two compound propositions. These two compound propositions are conjunctions of the components of U, conjunction of the components of U. Therefore, this is called disjunctive normal form of U, disjunctive normal form of U. So, disjunctive normal form of U is nothing but an equivalent compound statement which is disjunction of two or more compound statements. Those compound statements are conjunctions of the components. So, this is the disjunctive normal form. Now, we will see the conjunctive normal form, same. So, you will be given for any U compound proposition, if there exists a compound proposition V such that V is logically equivalent to U, condition number 1, and condition number 2 is V must be conjunction of, V must be conjunction. What is the symbol we use for conjunction? This is the symbol which we use for conjunction. Conjunction of two or more compound propositions, two or more compound propositions. These compound propositions are disjunctions of the components of U, disjunctions of the components of U. So, this is the R symbol, disjunction of the components of U. Let me explain one example. U is equal to P R Q and R. If I take U is equal to P R Q and R, then this is logically equivalent to, I am applying the distributive law for this one, P R Q and P R R. So, this is the equivalent compound proposition V. So, V is the equivalent compound proposition of U. Condition number 1 is satisfied. Condition number 2, V is conjunction of two compound statements. These two compound statements are disjunctions of the components of U, disjunctions of the components of U. Therefore, this is called conjunctive normal form of the given compound proposition. So, conjunctive normal form is an equivalent compound proposition of U which is conjunction of two or more compound propositions. These compound propositions are disjunctions of the components of U or their sometimes their negations also. And one more important point, this conjunctive normal form and disjunctive normal forms are not unique. So, for given compound proposition U, for the given compound proposition U, there may be more than one equivalent propositions which is conjunction of disjunction of the components or disjunction of conjunction of the components. So, this disjunctive normal form and conjunctive normal form, both of them are not unique, which means for the given compound proposition there may be more than one conjunctive normal form or there may be more than one disjunctive normal form. Now, we will see the laws of logics. These laws of logics will be helpful for you to find out the conjunctive normal form and disjunctive normal form. There are some laws of logics we will discuss one by one. The first one is to define these laws of logics, I am taking two statements P and Q. This is tautology and this is contradiction. We all know that the tautology is denoted with T naught and contradiction is denoted with F naught. Tautology is nothing but if any compound proposition is true for all possible truth cases, then it is called tautology. If the compound statement is false in all possible truth cases, then it is called contradiction. If it is mixed, sometimes it is true, sometimes it is false, then it is called contingency. So, to define these laws of logics, I am taking two statements P and Q. P and Q may be simple statements or compound statements. T naught is the tautology and F naught is the contradiction. So, now first one is idempotent law. Idempotent law. So, the idempotent law says that, so this is the idempotent law which is related to R connective, and this is the idempotent law which is related to AND connective. So, what is the idempotent law? P or Q is logically equivalent P. P or Q is logically equivalent to P, which is nothing but the disjunction of P and P is P only. Next, look at this. This is the second idempotent law. This is for AND connective. P and P is logically equivalent to P, which is nothing but the conjunction of P and P is logically equivalent to P. So, these laws are called idempotent laws. So, whatever laws of logics we are discussing, for every law there will be two sub laws. One is for R connective, another one is for AND connective. This is for R connective and this is for AND connective. The next one is identity law. The identity law says that, first one, P or F naught is logically equivalent to P, P and T naught is logically equivalent to P. So, the disjunction of P and F naught is P, the conjunction of P and T naught is P. Next one is inverse law. So, this is the inverse law for R connective and this is the inverse law for AND connective. So, P or negation P is tautology, P and negation P is contradiction. The next one is domination law. The domination law says that P or negation, P or T naught is T naught, P and F naught is F naught, P and F naught is F naught. That all these laws of logics will be proved with the help of the truth table. If you want to prove this, just construct the truth table for it. So, how to construct the truth table? There is only one simple statement and this is F naught, true, false. When only one simple statement is there, there will be only two possible truth cases, true, false. F naught means it is always false. So, what is P or F naught? P or F naught. P or F naught is false when both of them are false. P or F naught is false when both of them are false. So, in the last case only both of them are false, in the first case it is not. So, this P or F naught is logically equivalent to P. So, P or F naught and P are having same truth values, therefore, both of them are logically equivalent to each other. That is, P or F naught is logically equivalent to P. So, to prove all these laws of logics, we will be using truth table method. Now, we will see next one, commutative law. The commutative law says that P or Q, that means P or Q is logically equivalent to Q or P. When we take two statements P and Q, you can conject them in any order, either P and Q or Q and P, both of them are logically equivalent to each other. This is for R connective and this is for AND connective. This is the commutative law. Next one is absorption law. The absorption law says that P or P and Q is logically equivalent to P, P and P or Q is logically equivalent to P. So, what is the absorption law? Any one of the statement P must be repeated twice and there will be AND connective and there will be R connective. This is R connective and connective, then it is equivalent to P. Here P is repeated twice, AND connective, R connective, therefore it is P. These two laws are called absorption laws. The next one is De Morgan's law. The De Morgan's law says that negation of P or Q is logically equivalent to negation P and negation Q. If you expand this, if you expand the negation, then you will be getting this. This is for R connective and this is for AND connective. This is for R connective and this is for AND connective. And the next one is associative law. The associative law says that P or Q or R is logically equivalent to P or Q or R. If you take three simple statements, you can conjunct them in any order, either P or Q or R, or P or Q or R. So this is for R connective and this is for AND connective. And the last one is De Morgan's law. So the De Morgan's law, this is for this. There are two De Morgan's laws. P and R is logically equivalent to P or Q, and this AND will come here and this R will come here. So P or Q and R is logically equivalent to P or Q and P or R. The next one is P and Q or R is logically equivalent to P and Q or Q or R. The next one is the law of double negation. So the law of double negation means negation of negation, P is logically equivalent to P. The next one is the negation of conditional. So if you take a conditional statement, if you apply the negation of it, then you will be getting this. In the previous session I explained that P conditional Q is logically equivalent to negation P or Q. P and P conditional Q is logically equivalent to negation P or Q. If you apply the negation for it, take the negation on both the sides. P conditional Q, negation P conditional Q is logically equivalent to negation of negation P or Q. So this is logically equivalent to negation of negation P and negation Q. So this is logically equivalent to, from the double negation, negation of negation P is P, this is P and negation Q. So negation of P conditional Q is P and negation Q. So this is negation of conditional. This is the conditional. If you write the conditional statement in terms of R connective, this P conditional Q is logically equivalent to negation P or Q. So these are the laws of logics. If you want to prove the laws of logics, take the laws of logic, any one of the laws of logic, construct the truth table for the LHS and RHS. If LHS and RHS are having the same truth values, then we say that both of them are logically equivalent to each other. And these are the these are the laws of logics. Now we'll see some problems. We'll take some compound statements and we'll try to find out the disjunct to normal form and conjunct to normal form of the given compound proposition. The first one is this one. So here U is P and P conditional Q. P and P conditional Q. So this is logically equivalent to P and remove the conditional statement. If you remove the conditional statement, then it is negation P or Q. Negation P or Q. Just now we have seen the property. Look at the last one. Negation of P conditional Q is negation P or Q. I am applying this formula. So P conditional Q is negation P or Q. Next I am applying the distributive law. If you use the distributive law, this is P and negation P or P and Q. Now look at, this is the compound statement U and this is the equivalent statement V. If you observe both U and V are logically equivalent to each other, and V is a conjunction of two compound statements. These two compound statements are, disjunction of two compound statements. These two compound statements are conjunction of the components P comma Q or their negation. Therefore, this is called the disjunctive normal form of U. That is called the disjunctive normal form of U. Now I see some other example. We will find out the conjunctive normal form of this. So what is the conjunctive normal form? Conjunctive normal form is nothing but conjunction of two or more compound propositions. Those compound propositions are disjunctions of the components of U or their negation. So whatever statement they have given, I am taking this as U. U is equal to negation P conditional OR and P biconditional Q. So this is logically equivalent to negation P conditional OR and so this is the biconditional. So biconditional is a conjunction of two conditional statements, P conditional Q and Q conditional P. So now remove this by using this formula. P conditional Q is logically equivalent to negation P or Q. Now apply this formula and remove the conditional, then you will be getting this is negation of negation P or R and this is negation P or Q and this is negation Q or P. So this is logically equivalent to, from the law of double negation, negation of negation P is P, P or R and this is negation P or Q and this is negation Q or P. Now observe it, this is the equivalent compound proposition V. So U is the compound proposition and V is the equivalent compound proposition. Here V is a conjunction of three compound propositions. These three compound propositions are disjunctions of the components of U or their negations. Disjunctions of the components of U or their negations. Therefore, this is called disjunctive normal form of U. That is called disjunctive normal form of U. So this is how we are going to find out the disjunctive normal form, and this is conjunctive normal form, not disjunctive normal form. This is the disjunctive normal form of this. This is the this is the conjunctive normal form of this, and this is the disjunctive normal form of this. So this is how we are going to find out disjunctive normal form and conjunctive normal form. Now you see next one. So the next one are principal normal forms. So like normal forms, we have two principal normal forms. One is, so before we are going to define this principal disjunctive normal form, principal disjunctive normal form and principal conjunctive normal form. The first one is principal conjunctive normal form, second one is principal disjunctive normal form. Before we are going to define them, let us discuss what are min terms and max terms. We will discuss min terms and max terms. So to discuss min terms and max terms, I am taking two simple statements. So I am taking two simple statements P, Q. If you take two simple statements, then we will be having 2 power 2 min terms. 2 power 2 min terms. What are the min terms? P and Q is one min term, negation P and Q, negation P and negation Q, and P and negation Q. These are called min terms. So min terms are nothing but conjunctions of P and Q and their negations. Conjunction of P and Q or their negations are called min terms. This is one min term, P and Q. This is negation P and Q. This is negation P and negation Q, and this is negation, P and negation Q. So min terms are nothing but conjunctions of the simple statements. Now you see what are the max terms. So the max terms, P and Q are two simple statements. For these two simple statements, we will be having 4 max terms. The first one is PRQ, the second one is negation PRQ, the third one is negation PR negation Q, and the last one is PR negation Q. So max terms are nothing but disjunctions, disjunctive statements, disjunction of P comma Q are their negations. So min terms means conjunctive statement, max terms means disjunctive statements. Based on min terms and max terms, we are going to define the principal conjunctive normal form and principal disjunctive normal form. First let us see what is principal disjunctive normal form. We will see what is principal disjunctive normal form. So it is similar to the normal forms. You will be given the compound statement U. you will be given the compound statement U. You need to find out the equivalent compound proposition V such that V is logically equivalent to U, and the condition number 2 is V must be disjunction of min terms. Disjunction of min terms. So, for any given statement U, find the equivalent statement V. Find the equivalent statement V. What is V? V must be disjunction. What is the symbol we use for disjunction? This is the disjunctive symbol. Disjunction of two or more min terms. Min terms are nothing but conjunctive statement. Min terms are nothing but conjunctive, like P and Q or negation P and Q. Depends on the problem, you will be getting the min terms. So, principal disjunctive normal form is nothing but disjunction of two or more min terms. Disjunction of two or more min terms is called disjunctive normal form. Now, let me explain one important point here. For any two simple statements, there will be only 4 possible min terms. So, if there are only 4 possible min terms, if U is given, then whatever equivalent proposition we are finding, that must be having any one of the min terms. Sometimes all of them or some of them. So, this principal disjunctive normal form is always unique. You can follow any procedure, but whatever principal disjunctive normal form we are going to get it, that will be unique for irrespective of the procedure. So, this principal disjunctive normal form is unique. Now, look at what is principal conjunctive normal form. So, principal conjunctive normal form is nothing but conjunction of max terms. What is principal disjunctive normal form? So, principal disjunctive normal form is nothing but disjunction of principal disjunctive normal form is nothing but disjunction of min terms. Disjunction of min terms is called principal disjunctive normal form. So, principal conjunctive normal form is nothing but conjunction of max terms. Conjunction of max terms. So, disjunction of principal disjunctive normal form is nothing but disjunction of min terms. Principal conjunctive normal form is nothing but conjunction of max terms. So, this is about the principal conjunctive normal form and principal disjunctive normal form. Both of them are unique. Principal disjunctive normal form and principal conjunctive normal form, both of them are unique. If you follow truth table method or some other method, you will be getting only one principal disjunctive normal form and one principal conjunctive normal form. Now, we will see the problems. So, here I am taking some compound statement, that is P or P and Q. So, I am taking the statement P or P and Q. So, this is the compound statement U, that is the compound statement U. So, you need to find out the principal disjunctive normal form. Principal disjunctive normal form is nothing but disjunction of min terms. What are the min terms? These are the min terms. Min terms are nothing but conjunctive statement. Max terms are nothing but disjunctive statement. So, they have given the compound statement. The given compound statement is this P or P and Q. So, you need to find out the principal disjunctive normal form of this. Principal disjunctive normal form of this. That means, you have to find out the equivalent compound proposition V, which is disjunction of which terms? Disjunction. This is the disjunctive symbol, or is the disjunctive symbol, disjunction of min terms. You need to find out the disjunction of min terms. What are the min terms? This is one min term, negation P and negation Q is one min term, negation P and Q is one min term, and the last one P and negation Q. These are the min terms. So, you need to find out the equivalent compound proposition of this, which is the conjunction of these min terms. So, now this is logically equivalent to. So, what I am doing, so this is the statement U. Now, I am using the identity law. So, what is the identity law? P and T naught. P and T naught is logically equivalent to P. So, whatever P they have given, that can be conjected with T naught. If you conject P with T naught, you will be getting same P. So, P and T naught is, this is logically equivalent to P and T naught or P and Q. Now, next step. So, here already pre-proposition is present here. I am taking T naught in terms of Q. So, the given compound statement is having only two simple statements, one is P, another one is Q. So, here P is there, T naught I am taking in terms of Q. So, what is T naught? Tautology. What is tautology? For any statement Q, Q or negation Q is called tautology. So, Q or negation Q. Next, what I am doing? I am applying the distributive law. So, the distributive law, from the distributive law, this is logically equivalent to P or Q or, sorry, P and Q or P and negation Q. So, when we apply distributive law, then you will be getting these two compound propositions. Now, observe these compound propositions. This is one compound statement, this is one compound statement, and this is one compound statement. There are three compound statements. So, this is the equivalent compound proposition. This, if you simplify this, this is P or Q, P and Q, and this is P and Q. So, from the idempotent law, P and Q or P and Q is P and Q only. Now, this is one compound statement and this is one other compound statement. This is the logical equivalent statement of U. When we observe this, this is disjunction of min terms. This is disjunction of min terms. Therefore, this is the principal disjunct to normal form. This is the principal disjunct to normal form of the given statement. Similarly, next. Now, let's see what is principal conjunct to normal form. So, what is principal conjunct to normal form? Principal conjunct to normal form is nothing but conjunction of the max terms. What are the max terms? These are the max terms. Max terms are nothing but disjunct to statement. So, this is the given compound proposition U. This is U statement. I am taking this as U. Here I am applying the identity law. So, there are two identity laws. One is P and T naught is P, another one is P or F naught is P. So, P or F naught, I am leaving this as it is. Next, already P is present here, I am taking F naught in terms of Q, then it is Q and negation P. Apply the distributive law, then you will be getting this. Simplify this, then you will be getting this, because here P or Q, this is P or Q, this P or Q, both of them are same. Therefore, I am removing the duplication by applying the identity property, then you will be getting this. P or Q, this is one compound statement and this is one other compound statement. So, this is a U statement and this is V statement. V is the logical equivalent to U and V is a conjunction of two max terms. Conjunction of two max terms. Therefore, this is called principal conjunct to normal form. This is called principal conjunct to normal form. So, we are finding the principal conjunct to normal form and principal disjunct to normal form with the help of the laws of logics. Next important one. So, this is some other problem. Same, if two simple statements are given. So, PCNF is nothing but principal conjunct to normal form. I am applying the identity law for P and Q as well. Negation P or F naught, Q or F naught. Here negation P is present, I am taking F naught in terms of Q. Here Q is present, I am taking F naught in terms of P. Then apply the distributive law. So, this is equivalent to this and this is equivalent to this. Simplify this, then you will be getting this. If you observe this, this is one max term, this is one max term, this is one max term. So, this is the equivalent compound proportion of U. V is a conjunction of 3 max terms. Therefore, this is principal disjunct to normal, conjunct to normal form of the given compound statement. Now, the next topic is rules of inferences. This under these rules of inferences, we will discuss about the argument. So, let us consider some premises P1, P2, some simple statement. Premises are nothing but simple statements. I am taking n simple statements P1, P2 and so on n, and one more simple statement Q. Then the conditional statement P1 and P2 and so on and Pn conditional Q is called argument. This argument can be written like this also: P1, P2, P3 and so on Pn, therefore Q. This is argument. What is the argument? Argument is a conditional statement in which the LHS is conjunction of the simple statements, RHS is conclusion. So, this P1, P2 and so on Pn are called premises. P1, P2 and so on Pn are called premises, and the Q is called conclusion, and this is called conclusion. So, in every argument there will be some premises and there will be the conclusion. So, P1, P2 and so on Pn are the premises and Q is the conclusion. So, this argument is a conditional statement in which the LHS is conjunction of the premises and the RHS is conclusion. Now, we will discuss about the consistent and inconsistent premises. So, here I am taking some premises P1, P2 and so on Pn are the premises. When we say that these premises are consistent, if these premises are said to be consistent if the conjunctive statement is true in at least one case. If you take the conjunction of the premises, if the conjunction of the premises is true in at least one case, then we say that those premises are called consistent. Inconsistent means if the conjunction of the premises is always false. If the conjunction of the premises is always false in every case, if the conjunction, this is the conjunction of the premises, if this conjunction of the premises is false in every possible situation, then it is called inconsistent premises. So, every argument will be having some premises and some conclusion. Find the conjunction of the premises. If the conjunction of the premises is true in at least one case, then those premises are called consistent premises. If the conjunction of the premises is false, then it is called inconsistent premises. So, this is about consistent and inconsistent premises. Now, we will see what is the argument. We have already seen argument. Now, we will see what is the valid argument. The argument can be valid or invalid. Now, we will see what is the valid and invalid argument. So, I am taking some argument with the premises P1, P2 and so on Pn and the conclusion Q. So, then these are the premises P1, P2 and so on Pn and Q is the conclusion. Now, this argument is said to be valid argument if whenever each of the premises is true, the conclusion is likewise true. So, take the conjunction of the premises. If whenever this conjunction of the premises is true, if the conclusion is also true, then we say that the given argument is valid. So, this is the argument P1 and P2 and so on and Pn. Conditional Q. This is the argument and these are the premises and this total one is conjunction of the premises. Whenever this conjunction of the premises is true, if Q is also true, then we say that this is the valid argument. Otherwise, we say that it is invalid argument. Simply we can say that the valid argument means if you are able to derive the conclusion from the conjunction of the premises. Here this Q is conclusion, right? If you are able to derive the conclusion from the conjunction of the premises, then it is called valid argument. This is one definition. Now, I will see the another definition for valid argument. So, the other definition is, look at, an argument with premises and conclusion Q is valid if the conjunction of the premises is true, then the conclusion is likewise true. When we take the conjunction of the premises, if the conjunction of the premises is true, if Q is also true, then we say that the argument is valid. The other definition. So, if you look at this, this is the argument, right? So, the argument P1 and P2 and so on and Pn conditional Q. So, what is the definition of valid argument? Whenever the conjunction of the premises is true, the conclusion must be true. So, if you observe this, this is the definition of the logical implication. We already discussed the logical implication. What is logical implication? Whenever U is true, if V is also true, then we say that U is logically imply V. So, here this is conjunction of the premises is U and Q is the argument conclusion. Whenever this conjunction of the premises is true, then conclusion is also true. So, whenever the conjunction of the premises is true, if the conclusion is also true, then that is the valid argument, which is nothing but logical implication. So, if this is valid argument, then the LHS is logically imply RHS. Logically LHS is logically imply RHS. What is LHS? The conjunction of the premises. If this conjunction of the premises is true, if conclusion is also likewise true, then it is logical, then it is valid argument. So, these are the three definitions for valid argument. Now, look at this point. It is clear that the premises are always taken to be true. So, P1, P2 and so on Pn, these are all premises. These premises will be taken true always. The premises is always taken true, but the conclusion may or may not be true. So, whenever the conjunction of the premises is true, the conclusion may be true or may not be true. If the conclusion is also true, then it is called valid argument. If the conclusion is false, then it is called invalid argument. So, how to test whether the given arguments are valid or not means, take the conjunction of the premises, and if the conjunction of the premises is true, if the conclusion is also true, then it is valid argument. When the conjunction of the premises is true, if the conclusion is not true, then it is invalid argument. So, this is about valid and invalid argument. Now, we will see how to prove the consistent and inconsistent premises. So, these are some, I have taken some premises. This is one premises, this is one premises, this is one premises, and this is one premises. Now, I am going to find out the conjunction of the premises. So, there are three simple statements, and you will be having 2 power 8 truth cases, and these are all the 2 power 8 truth cases. This P conditional Q statement is false when the LHS is true, RHS is false. In this case, it is false. Next, in this case also it is false. In all other cases, it is true. Similarly, this P conditional OR, P is true, OR is false. Second case it is false. Next, third case it is false. In all other cases it is true. In all other cases it is true. Next one is Q conditional negation OR. This is negation OR, this is Q. Q conditional negation R is false. When Q is true, negation R is false. In this case it is false. Next, in this case also it is false. In the remaining cases it is true. Now find the conjunction of all these premises. This is premises 1, premises 2, premises 3, and this is simple OR is the premises 4. I am taking the conjunction of all these premises. The conjunction of all these premises is true when all of them are true. All of them is this R must be true, this must be true, this must be true, and this must be true. If all of them are true, then this conjunctive statement is true. Now look at first case. This R is true, P conditional Q is true, this is true, this is not true, therefore it is false. Next, in the second case, R is false, therefore it is false. In the third case, R is true, therefore it is false. In the fourth case, R is false, therefore it is false. In the fifth case, R is true, P conditional Q is true, this one is true but this is false, therefore it is false. Next case, R is true, this one is true, this one is true, this one is true, therefore it is true. In next case, next two cases it is false. So here the conjunction of the premises is true in last, that is sixth case. Here R is true, P conditional Q is true, P conditional R is true, Q conditional negation R is true. So therefore it is true. So we have found the truth values for the conjunction of the premises. Now see what are the definitions of consistent and inconsistent premises. If the conjunction of the premises is true in at least one case, then they are called consistent premises. So the conjunction of the premises is true in this case, therefore whatever premises they have given, they are consistent premises. Now I'll see one more example. Now this is another example. So here they have given some premises 1, 2, 3, 4. We will find out the truth values for conjunction of the premises. P conditional Q is false in third case and fourth case. In all other cases it is true. Next one is P conditional R. P conditional R is false in second case. Next, this fourth case, in all other cases it is true. Next, Q conditional negation R. Q conditional negation R is false in this case. Next, in this case, in the remaining cases it is true. Now I am finding the truth values for conjunction of the premises. This is 1, this is 2, this is 3, and the last one is P, this is 4. So this is the conjunction of the premises. This conjunction of the premises is true if all of them are true. When we observe all of them, in none of the cases they are true. If you look at P is true, 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 false, therefore it is false. Next, true, true, false, true, therefore it is false. All of them are not true. True, false, true, false, all of them are not false, true, therefore it is false. True, true, sorry, not this one, true, false, false, true, all of them are not true, therefore it is false. Next, false, true, true, false, all of them are not true, therefore it is false. In all other cases, the conjunction of the premises is true. That means the conjunction of all the premises is always true. Therefore, it is inconsistent premises. So this is how we are going to test whether the given premises are consistent or not. Construct the truth table for the conjunction of the premises. If the conjunction of the premises is true in at least one case, they are consistent premises. If the conjunction of the premises is true in all cases, then they are called inconsistent premises. This is all about today's session. In today's session, I explained about special connectives, I explained about normal forms, principal normal forms, logical implication, loss of logic, and valid, invalid arguments, consistent and inconsistent premises. Thanks for watching the video.